Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 2 for this week. I'm actually doing this one day early to more or less get it out of the way, but it's still something I definitely wanted to do, and I hope you'll find interesting. Every once in a while I'll do a bonus weather video that is a little bit more mathematically intensive, but I will try to make it as understandable as I can because I have confidence that if things are explained properly, that anybody can understand it. It isn't a matter of it being exclusive to a certain part of the population. I think everybody can understand something. It just depends on how well it's explained. Whether or not I do a good job at that or not, I will leave up to you at the end of this. All right, so we're going to talk about divergence, convergence, and vertical motion, all of which are going on all the time in the atmosphere. So we're going to be taking a look at the wind in 3 dimensions. Okay, so there is something called the continuity equation, which basically talks about the fact that mass must be conserved, okay? And so the equation for that is du dx plus dv dy plus dw dz equals 0. Now, what does all that mean? Well, every time you see a d, just think of it as being a change or a delta, okay? How something is changing over time. The U is what we call the west to east component of the wind, okay, like this. The V is the north-south component of the wind that's going south to north. And the dW, dz, is how the vertical motion, the air going up or down, is changing as you go up through the atmosphere, okay? When you add up all those three, all those changes have to be equal to 0 in order for mass to be conserved. So again, U is the west to east component of the wind, V is the south to north component, and W is the vertical wind or vertical motion. All right, so let's talk about divergence and convergence here. At the little blue dot, if you have a light wind from the west and a stronger wind from the west to the east of that location, and the lighter wind is to the west, then you have divergence going on because you're removing more mass to the east than you are bringing in from the west. So this is an example of divergence. Now, the opposite is true here, where you're bringing in more mass from the west than you are taking away to the east, and so at that blue dot, we call that convergence. It is exactly the same for the V component of the wind, except now the arrows are oriented north-south instead of east-west, okay? So, let's go back now to our original equation, and we're going to call the first 2 terms in that equation the horizontal divergence. In other words, you're combining the divergence, or convergence for that matter, east-west and north-south, but it's all at one level, okay? So we're going to call that the horizontal divergence, and if you solve for that, then the horizontal divergence is equal to minus the change in the vertical motion with height as you go up, okay? So if there is horizontal divergence going on, then the vertical motion is becoming increasingly negative as you go past that point, okay? If there is horizontal convergence, which is negative divergence, then the vertical motion is going to be increasing as you go up past that particular point, okay? So again, just to reiterate, if there is horizontal divergence at any level, then the vertical velocity must be trending more negative with height as you pass that point. And if there is horizontal convergence at any one level, then the vertical velocity must be trending more positive with height. Okay, you with me? So let's now talk about divergence and vertical motion. In this case, we have convergence in the high levels of the atmosphere. The air can't go up because, to make a long story short, the tropopause, or the boundary between the troposphere and the stratosphere, is very stable, and it prevents the air from going upwards. So it really has no choice but to go down. And of course, when it hits the ground, it can't keep going into the mud, and so it spreads out and diverges, okay? Here's the opposite situation, where you have upper level divergence, the wind spreading apart. That induces air going up to replace it, and that means the air has to come together in the low levels, or converge in the low levels, in order to resupply the mass. So on the left, upper level divergence, low level divergence, upper level convergence, leading to sinking motion, which usually leads to warming and drying. And then on the right, we have low level convergence, upper level divergence, which leads to rising motion and clouds and precipitation. So is the horizontal divergence ever 0? Well, if there is convergence or divergence at the upper levels and divergence, convergence at the lower levels, then there's got to be a place in between where the sign of the divergence changes from positive to negative or negative to positive. We call this the level of non-divergence. And so if you think of our original equation, if the divergence, the horizontal divergence, is equal to 0, which is what the level of non-divergence would imply, then that means that dw dz has to be 0, which means that the vertical motion is no longer changing with height. So it has reached a maximum at that particular level, okay? So if the vertical motion is no longer changing, then the maximum upward or downward motion occurs at the level of non-divergence. So if the air is coming together at the bottom, it starts to go up, and it goes up faster and faster and faster and faster, and it reaches its max at the level of non-divergence, and then above that, it starts to decrease, and when it gets to the top of the troposphere, it's basically 0. Okay? Now, it is a little bit different with thunderstorms because the force of buoyancy is involved here. When an air parcel starts to rise, if it's warmer than its environment, it's buoyant, and buoyancy is a force. And you remember force equals mass times acceleration. So if there's a force, there's got to be acceleration. So that air accelerates upward and upward and upward and upward, and it's going like a house afire. And in a good old-fashioned barn burner thunderstorm, it can keep going up or accelerating upward all the way up to 40, 50, or even 60,000 feet. So as long as it's accelerating, then there's got to be horizontal convergence going on. And so in a thunderstorm, the convergence is over a much, much deeper layer, okay, because you have to go all the way up to 40, 50, 60,000 feet in order for the maximum vertical motion to be achieved. And so, again, the convergence would occupy a much, much deeper layer. The divergence at the top of the thunderstorm can still be very strong, but it doesn't occupy that much vertical space, okay? The amount of, or the distance where the layer in which convergence is going on in a thunderstorm horizontally is much, much deeper than the layer of divergence at the top of the thunderstorm. Okay. Did any of that make sense? Well, actually, I forgot to put it up here verbally for you, or in text. So, again, the level of non-divergence is much higher with a thunderstorm, and so convergence extends over a very deep layer. Maybe I should have just put that up and shut up. All right, so that is it for today. I hope at least a small percentage of that made sense. If it doesn't, let me know, and I'll try to clarify some things. But that is bonus weather video number 2 for this week. Hope it made some sense for you. You all have a wonderful weekend coming up, and we will talk to you again next week on Monday. You all take care, everybody. See you later.